Hello, I'm glad you said see you again. And let's start our lectures on hypersonic flow. Today we have lecture number 11, and the topic of this lecture, viscous hypersonic flow. As you already know, in this part 2, we emphasize the effects of viscosity. And except viscosity, we emphasize thermal conduction in combination with high Mach number. And we will label such flows, namely as hypersonic viscous flow. The effects of high temperature and diffusion will be covered in next part number 3. In dealing with inviscid hypersonic flow in previous part, we examined the question, what happens to the fluid dynamics of an inviscid flow when the Mach number is made very large? So in part 2, we take the next logical step and address the question, what happens in a high Mach number flow when the transport phenomena of the viscosity and thermal conduction are included? The answer to this question leads to many practical results regarding to prediction of skin friction and aerodynamic heating in hypersonic flow. So let's study some basic aspects, viscous flow and boundary layers result and aerodynamic heating. With this module, we leave the ideal world of inviscid flow and enter the real world of viscous flow. What physical phenomena determine the skin friction drag and aerodynamic heating of hypersonic vehicles? We will find out here answer to this question. How can we calculate the skin friction drag and aerodynamic heating of hypersonic vehicles? If you are a practical person looking for a practical method to deal with skin friction drag and aerodynamic heating, then you will eventually feel at home in this chapter, in this. To get to the point, however, we have to note some rather interesting theoretical consideration. We have to start with the governing continuum, momentum, and energy equation for a viscous flow. And the Navier-Stokes equation, and then specialize these questions for the case of flow in a boundary layer, the boundary layer equation. Both of these systems of equation are coupled nonlinear partial differential equation. The difference being that the Navier-Stokes equation have no analytical solution, whereas the boundary layer equation being simple. lend themselves to a partially analytical approach that provides practical results for skin friction drag and heat transfer. If you are a person who enjoys analysis and working with equations, you will immediately feel at home with the first part of this. But now, in short, this module is where the rubber hits the road, where some of the most important aspects of hypersonic aerodynamics come into play. So in this module, you are entering a different world, a world where friction and thermal conduction reign. This is not an easy world, but if you treat it with seriousness and respect, it will reward you with brand new vistas in hypersonic aerodynamics. So the matter of aerodynamic heating, hence skin temperature, and shear stress, the same hence skin friction drag, is an extremely important aspect of hypersonic vehicle design. This has never been truer than in the modern hypersonic applications of today. For example, consider the concept of an aerospace plane designed to take off horizontally from an existing runway and then literally blast its way into orbit, mainly on the strength of air-breathing propulsion. For example, researchers have made engineering estimates of the aerodynamic heating to an aerospace plane for both ascent and re-entry, and compared this result with the space shuttle re-entry. These results are summarized in the bar chart shown in this slide, which gives both the maximum heat transfer rate in watt per square centimeter and the total heat transfer in kilojoule at the stagnation point. Here we see the striking result that the aerospace plane re-entry stagnation point heating is 3 times larger than the re-entry heating of the space shuttle. And even more striking, the ascent heating of the aerospace plane is an order of magnitude larger than re-entry heating of the space shuttle. Hence, because the requirements of the aerospace plane to achieve essentially orbital velocity within the atmosphere, the aerodynamic heating during ascent dominates its design. Another example, this time emphasizing the role of skin friction drag, is given in this figure. Here, a hypersonic wave rider design to optimize the lift to drag ratio is shown here. Such wave riders are promising hypersonic cruise vehicle configuration, wherein a high value of lift to drag is necessary for efficient, long-range cruising conditions. Now let us continue to examine the importance of hypersonic viscous flow, but from a slightly different point of view, emphasizing a more purely fluid dynamic aspect. Consider this diagram which is a velocity-altitude map showing several lifting re-entry trajectories from orbit, each with different values of the lift parameter measured m over CL times S. The shaded portion corresponded to re-entry of the space shuttle. Note that the higher altitude portions of the flight trajectory experience combined conditions of high Mach number and low Reynolds number conditions that accentuate the effects of hypersonic viscous flow. Indeed, for most of the re-entry trajectory, a hypersonic vehicle is going to experience important Reynolds number effect. Also note that a fully arbitrary transition Reynolds number of 10 in power 6 is assumed, so that regions of fully laminar flow and of turbulent flow for a 10-meter long vehicles are identified on the right of this figure. The main thrust of proposed figure is to indicate that viscous effects are important in hypersonic flight. In the present lecture, some basic aspects of viscous flow will be discussed, including the full governing equation, I mean the Navier-Stokes equation, the boundary layer equation, and how they are affected by hypersonic conditions, and important results from the boundary layer equation. Return for a moment to the general roadmap in this slide. We have completed our discussions on inviscid flows listed under the left-hand columns in the proposed slide. A more detailed roadmap for this lecture is given in this slide. The Navier-Stokes equations are the general governing equation for viscous flow, and we start with them. From this equation, we extract the similarity parameters for compressible viscous flow, one of the most fundamental of consideration. We also examine the boundary conditions that necessarily go along with the Navier-Stokes equation. Then we introduce the concept of a boundary layer, one of the most important intellectual concepts in fluid dynamics. Conceived by Ludwig Prandtl in 1904, the boundary layer is the region adjacent to a surface where the effects of friction and thermal conduction are dominant. The flow external to the boundary layer, however, is not greatly affected by such effects and can be treated as inviscid. This division of a fluid flow into two distinct regions, the viscous boundary layer adjacent to the surface and inviscid flow external to the boundary layer, is arguably the most important intellectual advancement in fluid dynamics since the beginning from the 20th century. As shown in this slide, our discussion on boundary layers then divides into four theories. The first is the derivation of a boundary layer equation. And for a laminar compressible flow, followed by a discussion of the two classes of solution of this equation. Self-similar solution, giving results for flow over a flat plate and around a stagnation point. And the more general, no similar solutions for general configuration. Then we move to the second. Heading and discuss the phenomena of transition from a laminar to a turbulent boundary layer, followed by the third heading, and namely turbulent boundary layer. Using the classic result from incompressible flow, boundary layer transition, and turbulent boundary layer. For all subject items in the roadmap in proposed slide, the special aspects of hypersonic flow will be highlighted and I hope discussed. Okay? So let's go on. First questions for today's lecture: governing equation for viscous flow, and namely Navier-Stokes equation. Euler equations are, in reality, a special form of the general governing equation of fluid dynamics, wherein the viscous terms have been deleted. Another way of stating this is that the Euler equations are the limiting form of the general viscous flow equation in the limit of infinite Reynolds number. Indeed, it is frequently convenient to think of inviscid flow as a flow that results from the Reynolds number approaching infinity. So, in the general equations of motion for a fluid flow, viscous effects do not influence the basic principle of mass conservation. However, visualizing a moving fluid element, the shear and normal viscous stresses on the surface of the element result in stress terms that appear in both the momentum and energy equation. Moreover, thermal conduction across the surface of the element provides an additional mode of energy transfer, which appears in the energy equation. The resulting governing equations called the Navier-Stokes equation. I hope you remember. So, that's containing next continuity equation, x, y, and z momentum, and energy equation, you can see here. Yes? And where that's tau, we have x, y, tau, y, z, and tau z, x. The preceding equations are written for an unsteady, compressible, viscous, and three-dimensional flow in Cartesian coordinates. Okay? Please adjust in coordinates. In addition to the familiar symbols, we now have the shear stresses of the three components, tau xy, tau yz, and tau zx, and the normal viscous stresses, and you see the right part, tau xx, tau yy, tau zz, which are related to velocity gradients in the flow via our previous equation. Also mu in both viscosity, this is viscosity coefficient. K is the thermal conductivity. And lambda is the bulk viscosity coefficient, where the usual Stokes hypothesis lambda equals minus 2 over 3 times mu. In the energy equation on the top of this side, E is the internal energy. As you can see here, E, yes, is internal energy per unit mass. Q dot here, as we can see, this one represents the volumetric heating that might occur, say by the absorption or emission of radiation by the gas. And the temperature gradient, d over dx, yes, as you can see, d over dx, and another coefficient, represent energy transfer across a surface caused by the thermal conduction. You know, historically the term Navier-Stokes equation identified only the momentum equation, because these were the very equation derived by the Frenchman Claude Louis Navier in 1827, and independently by the Englishman George Stokes in 1844. However, in recent times, particularly with the advent of computational fluid dynamics, most citations of the literature referring to the solution of the Navier-Stokes equation denote solution of the complete systems of equation, namely equation on the right part of this slide. We will follow this modern trend here, and we'll label the complete systems of equation for viscous flow, so continuity equation, momentum, and energy equation, as the Navier-Stokes equation, okay? Just as in case of the Euler equation, there is no general analytic solution to the complete Navier-Stokes equation. However, in analogy with the approximate solution of the Euler equations, we can simplify the Navier-Stokes equations via an appropriate set of assumptions and obtain approximate viscous flow result. Now next topic today's lecture, similarity parameters and boundary conditions. As a precursor to the boundary layer equation to be discussed in the next module, and as a means to highlight the important similarity parameters for a viscous flow, it is useful to have a non-dimensional form of the Navier-Stokes equation. So, to reduce the number of operations and terms without loss of instructional value, we will consider a two-dimensional steady flow, and we will ignore the normal stresses tau xx and tau yy. So, let us introduce the following dimensionless variables on the top of this slide. Here we have rho infinity, v infinity, p infinity, mu infinity, k infinity, and t infinity. All these parameters are reference values. For example, say free stream values, and c is a reference length, say the core of an airfoil. In terms of these dimensionless variables, become for two-dimensional ratio of specific heat, we can find that gamma. Gamma is Cp over Cv. Mach number on the next expression, Reynolds number, and Prandtl number. These four-dimensional parameters, as you can see, ratio of specific heats, Mach number, Reynolds, and Prandtl numbers, are called similarity parameters and are very important in determining the nature of given viscous flow problem. Indeed, a formal method for identifying the similarity parameter in any mechanical system is to non-dimensionalize the governing equation. The dimensionless constant that appear in front of the derivative term are the governing similarity parameters. The significance of flow similarity and the meaning of the similarity parameters will be discussed in detail in our final lecture. We will make only a few brief comments here in the way of a reminder. First of all, from our experience with inviscid flow, as we already made in part 1, it is no surprise that gamma and M infinity carry over as similarity parameters for viscous flow. Thermodynamic properties, as reflected through gamma, are important for any high-speed flow problem. A combination of thermodynamic and flow kinetic energy can be found in M infinity. M infinity proportional flow kinetic energy and inverse proportional the flow internal energy. And if we study the Reynolds number, we have Reynolds proportional inertia forces and inverse proportional viscous forces. The Prandtl number, introduced via the energy equation, is an index that is proportional to the ratio of energy dissipated by friction to the energy transported by the thermal conductivity. That is, we may see Prandtl transformed in this field. The study of the compressible viscous flow, Prandtl is just as important as gamma, Reynolds, or Mach number. For air at standard conditions, Prandtl equals 4.71. Note that Prandtl is a property of the gas. For different gases, Prandtl is different. Also, like mu, K, and Cp, Prandtl for a non-reacting gas is a friction of temperature only. So, sorry, not friction, as a function of temperature. For a chemically reacting gas, Prandtl is also dependent on the local chemical composition, which in turn depends on the local temperature and pressure for an equilibrium flow, and on the history of the upstream conditions for a non-equilibrium flow. For boundary conditions, we can see at this left part of the slide on the top, U equals V equals 0. If there is mass transfer at the wall as a result of ablation or transpiration cooling, for example, then this equation is modified as follows. Both boundary conditions with mass transfer will be U equals 0 and V equals VW. V sub W is a specified velocity normal to the surface. In addition, because of energy transport by thermal conduction, we require an additional boundary condition at the ball involving internal energy, or more usually temperature. If the wall is a constant temperature, then the boundary condition is simple. Constant wall temperature boundary condition will be T equal T sub W, where T sub W denotes the specified wall temperature. As is more usually the case, the wall will not be at the constant temperature. If you know a priori the distribution of temperature along the surface, then our equation of the top is slightly modified as follows. Variable wall temperature boundary condition may be represented as this equation at the bottom. T proportional T sub W from S. And this T sub W over S is a specified wall temperature variation as a function of distance along the surface S. Unfortunately, in a high-speed flow problem, the wall temperature is usually one of the unknowns, and we cannot utilize either previous equation or at last next one. Instead, the more general condition of temperature at the wall is given by Fourier's law of heat conduction. Heat transfer wall boundary condition Q sub W proportions minus K coefficient times dt over dn over the V. Here the Q sub W is the heat transfer energy per second per unit area into or out of the wall. And here is the coordinate normal to the wall, perpendicular to that wall. And dt over dn is the normal temperature gradient existing in the gas immediately at the wall. In general, the wall heat transfer and hence the wall temperature gradient are unknowns for the problem. And therefore, in the most general case, the wall boundary condition must be matched to a separate heat condition analysis, describing the heat distribution within the surface material itself. And both the flow problem and the surface material problem must be solved in a coupled fashion. A special case of this equation is the adiabatic wall condition, wherein by definition the heat transfer to the wall is zero. So from this heat wall boundary condition, in this equation, we have in this case adiabatic wall condition dt to dn equals zero. Adiabatic wall condition. Note that here the boundary condition is not on the wall temperature itself, but rather on the temperature gradient, namely a specified zero gradient at the wall. The resulting wall temperature, which comes out as part of the solution, is defined as the adiabatic wall temperature, TAB, sub AB, sometimes called the equilibrium temperature. As a final note in this module, we observe that the non-dimensional Navier-Stokes equation in the limit of when Reynolds becomes to infinity reduced to the non-dimensional Euler equation. But thus, supporting our earlier statement that an inviscid flow can be thought of as a limiting case of a viscous flow when the Reynolds number becomes infinite. Okay? Next, topics today's lecture, boundary layer equation for hypersonic flow. You know, until the advent of computational fluid dynamics, exact solutions of the complete Navier-Stokes equation for practical problems were virtually non-existent. Even today, numerical solutions of this equation, it will be discussed a bit later, are not easy and generally require a lot of computer power, as well as human resources to generate the computer solution. Therefore, reasons for exist for simpler viscous flow solution. By a suitable order of magnitude reduction of the Navier-Stokes equation, a simpler set of equations, namely the boundary layer equation, can be obtained. The compressible boundary layer equations are the same, whether the flow is subsonic, supersonic, or even hypersonic, neglecting high temperature effect. Okay? So, however, this is one aspect of the standard boundary layer equation that becomes rather tedious at the supersonic speed, and that is not always recognized. Now, considering two-dimensional steady flow, the non-dimensionalized form of the X momentum equation, one of the Navier-Stokes equations, given by this, you can see on the top of this slide. Now, let us now reduce this a bit tedious equation to an approximate form that holds reasonably well within a boundary layer. So, consider the boundary layer along a flat plane of length d. The basic assumption of boundary layer theory is that a boundary layer is very thin in comparison with the scale of the boundary, so that we may write delta many times less than t. Here delta is the boundary layer thickness. Consider the continuity equation for a steady two-dimensional flow, which in terms of the non-dimensional variables is given by, from the previous slide, by this equation you can see in the middle. D from rho u over dx and plus d from rho v over dy should be equal to 0. Because u varies from 0 at the wall to 1 at the edge of the boundary layer, let us say that u hat is of the order of magnitude equal to 1 and symbolized as maybe as a u 0 from 1. Similarity for rho, you can see here, 0 from 1. Also because x varies from 0 to c, so the x will be at this value. However, because y varies from 0 to delta, where the delta less than c, then y is of the smaller order of magnitude, denoted by this expression. Without loss of generality, we can assume that c is a unit length. Therefore, y will be equal 0 from delta. Putting these orders of magnitude into our equation, we have this expression here. Hence, from this expression, clearly v must be of an order of magnitude equal to delta. That is v from equal 0 when we have from delta. Now, examine the order of magnitude of the terms in our equation, and we have got these two expressions on the top right corner of this slide. Hence, the order of magnitude equation can be written at the middle expression here. Let us now introduce another assumption of boundary layer theory, namely that the Reynolds number is large. Indeed, large enough such that 1 over Reynolds equals 0, dependence from delta square. Then our previous equation here on the middle, maybe become at the bottom one. With this one, okay? So, in terms of dimensionless variables, we can get this expression on the top of the left corner of the upper corner of this slide. Therefore, from the Y momentum equation, specialized to a boundary layer, we can write as expression very simple in classical. dp over dy should be equal 0. This equation is very important. It states that at a given x station, the pressure is constant through the boundary layer in a direction normal to the surface. And this implies that the pressure distribution at the outer edge of the boundary layer is impressed directly to the surface without change. And hence, throughout the boundary layer, P should be equal P from X and P epsilon is a pressure distribution on the edge of the boundary layer. All this determined from the inviscid flow calculation. Okay? So, this leads our to a major point concerning hypersonic boundary layer. And the reason for reviewing the preceding order of magnitude analysis of the boundary layer equation. Thus, for very large hypersonic Mach numbers, the assumption that P is constant in the normal direction through a boundary layer is not always valid. And this aspect of hypersonic boundary layers is not frequently discussed or even say widely appreciated, and hence some emphasis is being made here. Also, it is important to properly interpret the preceding statement. It is a fluid dynamic result which states that the normal pressure gradient through a hypersonic boundary layer need not be 0. Since even from middle 50s in 20th century, a large number of hypersonic boundary layer calculations have been made with the conventional boundary layer assumption. We mean that dp to dy should be equal to 0, and in many applications this is justified. However, we should not expect this to always be the case. Indeed, the question concerning the possible existence of a finite normal pressure gradient adds more support to carrying out hypersonic viscous flow calculation by going beyond the usual boundary layer calculation and instead dealing with the entire shock layer as fully viscous from the body to the shock wave. In such viscous shock layer analysis, the normal pressure gradient is calculated as part of the solution to the problem, and thus circumventing the uncertainty as the whether dp over dn is 0 or finite. Keeping the preceding consideration in mind, we will proceed in the present our lecture with a discussion of the conventional boundary layer equation and result based upon, namely, this equation. So, inserting E as H minus P over rho in this equation, subtracting the momentum equation multiplied by velocity and performing an order of magnitude analysis similar to those in the preceding, we can obtain the boundary layer equation in this form, as you can see in the middle of this slide. The details are left to you, okay? So, in summary, by making the combined assumption, namely delta less than C, and Reynolds not less than 1 over the delta sphere, the complete Navier-Stokes equations can be reduced to simpler forms that apply to a boundary layer. These boundary layer equations are as follows. So, it's continuity equation, x momentum, y momentum equation, energy equations, and note that, as in the case of the Navier-Stokes equation, the boundary layer equations are non-linear. However, the boundary layer equations are simpler, right? And therefore are more readily solved. And also, because P equals PE from X, the pressure gradient expressed as the dP to dx, and is re-expressed as the dPE to dx. And now, in the preceding equation, the unknowns are U, V, rho, and H. P is known from the P as a P from P sub E from X. And mu and K are properties of the fluid that vary with temperature. So to complete the system, we have for a calorically perfect gas. So we may write as the P equals rho RT. And H should be proportional Cp times T. Hence, all these equations before our death, yes, 1, 2, 3, 4, yes, are 5 equations for 5 unknowns, U, V, rho, T, and A, 5 unknowns. The boundary conditions for the preceding equations are as follows. So, at the ball, we have y equals 0, u equals 0, v 0, and t equals p sub w wall. For adiabatic wall, the adiabatic wall, we have dt to the n over that wall equals 0. So, at the boundary layer edge, we have this expression on the bottom. And we should note it here that because the boundary layer thickness is not known a priori, the boundary condition at the edge of the boundary layer is given at large y, essentially y approaching infinity. So the boundary layer equation just given apply to compressible flow. They are equally applicable to subsonic and even supersonic flow, with no distinction made for such cases. They can be, sorry, for 1 second, they can be and have been applied to hypersonic flow. Also, if M infinity is high enough, viscous dissipation within the boundary layer creates high temperatures, which in turn causes chemical reaction within the boundary layer. In such a case, the system of evacuation is not totally applicable. Diffusion of chemical species and energy changes. And all of this caused by chemical reactions and must be included too. Also, many hypersonic wind tunnel tests are conducted in cold flows, flows where the total enthalpy is low enough to ignore high temperature effects. And hence, there are many hypersonic applications where the governing boundary layer aviation for a calorically perfect car are appropriate. And thus, we will pursue various aspects of this equation throughout the remainder of our lecture. Okay? And this ends our introductory discussion of the basic aspects of the hypersonic viscous flow. So, also, return to the lecture roadmap in this slide. We have progressed about halfway down the map and have just finished the left-hand box labeled laminar flow boundary layer equation. Okay? We are ready to move to the first sub-item under this box, namely self-similar solution. The material we will discuss is somewhat classical in nature. It will be, for all practical purposes, a discussion of compressible boundary layer theory, not limited to just hypersonic flow. However, our interest here is in the application of the result of this classical theory to high Mach number problem. Are you agree with me? Okay. In this case, we can start another topic today's lecture. Another question, hypersonic boundary layer theory. And we will start with self-similar solution. Also, the title of this module involves the word hypersonic. But in reality, we will be dealing with compressible boundary layer theory. And the result will apply to both subsonic and supersonic, as well as hypersonic conditions too. As a reminder, a major aspect that distinguishes hypersonic boundary layer theory from the subsonic and supersonic cases is the intense viscous dissipation, resulting in high temperature, chemically reacting flow. In contrast, in the present module, as well as throughout part 1, previous part, we are assuming a calorically perfect curve. That is, we are highlighting only the fluid dynamic effect of viscosity and thermal conductivity in combination with high Mach number. In this regard, the present lecture is classical in its scope. The material discussed here has evolved since previous century, since 1940, when interest of compressible boundary layers began to emerge under the impetus of high-speed, subsonic, and even hypersonic flight. The concept of self-similar boundary layers is illustrated in this slide. In general, the variation of flow properties throughout a two-dimensional boundary layer is a function of both F, X, and Y. This is sketched in the physical plane shown at the left of this slide, where two velocity profiles are shown at different x locations, namely x1 and x2, along the surface. In general, the profiles are different. That is, we have a u variating from xy, so should be equal u as variation x, 2, and 1. However, for certain cases, under the appropriate independent variable transformation from x and y to j and h, the flow field profiles become independent of location along the surface. And this is sketched at the right of this slide, which shows a transformed plane wherein the velocity profile is independent of the transformed surface distance j. That is, the same velocity profiles exist at different values of j, say j1, j2, and so on. And thus, in the transformed plane, the velocity profile is given by u as u from h, independent of j. Boundary layers that exhibit this property and called self-similar boundary layers, and solutions for these boundary layers are called self-similar solutions, the subject of this model. Self-similar solutions to boundary layers have been investigated since the original incompressible flat plate solution obtained by Clausius in 1908. Many years ago, before we can move in with hypersonic flight. The fact that the flow might be hypersonic does not preclude the occurrence of the self-similar solution, as we will see. Let us now transform the boundary layer equation, which you have seen in previous module, today from physical x and y space to a transformed space j and h space, and examine the possibility of self-similar solution. So, the transformation here is that zeta, and eta. Here we have some expression with e, r, e, u, e, and me are the density, velocity, and viscosity coefficients, respectively, at the edge of the boundary layer. So E, it means edge. Because R sub E and U sub E and me are function of X only. And since J will depend only from X. And hence the transformation given by our equation will be called the least Dorodnitsin transformation in our lecture. Also, the following transformation might be at first look involved. They are in reality quite straightforward. You know, there are 4 basic steps to the transformation process, leading to the final transformed equation. These 4 steps will be clearly identified next for the convenience of our studying process. Let's start with the step 1, namely transformation of the independent variable. The independent variable transformation given by equation and must be couched in terms of derivatives because terms involving x and y in the original boundary layer equations are derivative terms. From the chain rule of differential calculus, we have expression for d over dx and d over dy on the middle of this left side of this slide. From the previous equations, keeping in mind that the zeta is dependent from x2, we have only from x, we have next expression in this case. After substitution, we obtain the following derivative transformation. And at this stage, it is convenient, but generally speaking, not necessary, to introduce the stream function psi defined as usually. So we can find function psi d psi to dy equals rho u, and d psi to dx, it's minus rho b. In terms of psi, the x momentum boundary layer equation becomes in next form. You can see in this expression on the left part of the bottom of this slide. Introducing the derivative transformation into this equation, we have got this large expression here. Multiplying this equation by square root from 2 zeta over u sub e times rho, we can obtain a bit simpler equation, but not very nice. Yes, a bit simpler. And this equation is the end of our step 1, transformation of the independent variable. Namely, this equation represents the boundary layer x momentum equation in terms of the transformed independent variable. Next step, step 2, transformation of the dependent variable. So here, let us define a function of zeta, and eta as a function from zeta and eta, such as we can see here on the first expression. Here the prime denotes, for the time being, the partial derivative with respect to eta. Eta, here, Greek letters eta. So, recalling that the velocity at the edge of the boundary layer is function of x, and here function of x, and here as a function of zeta only, that is, we may rewrite that u sub e is a function from zeta. And we can write next series expression you can see here. Next two expressions here. Here we have f double stretch denoted as a d2f over d eta squared. Second derivative. First derivative and second derivative. Okay. Next, step 3, identification of v with psi. The new dependent variables from function of zeta eta, defined by our previous equation, is essentially a stream function in its own right, and is indeed related to psi as follows. So we may rewrite our equation in this form here. As we can see, it's the left part a bit tough, but very simple. Another rho u or rho f dot f stretch of times u sub e. Or we may rewrite d psi to d eta as square root from 2 zeta times first derivative from f. Integrating this equation with respect to eta, we can get expression on the top. Here, function f is an arbitrary function of zeta. However, recall from the general properties of the stream function that with no mass injection at the wall, the value of psi at the wall must be equal 0, right? That is, psi from zeta at 0 must be equal 0. Okay? So, in our equation, last equation, applied to the wall, the only way to ensure that psi equals 0 at each point along the wall is for each terms to be 0. And that is both f equals 0 and f capital should be equal 0. And hence, the arbitrary function must be 0. So we may write as the next expression for psi, if psi proportional square root from 2 zeta times f. Clearly, from this equation, f is a stream function related to psi. Okay? And finally, from this equation, we can get this last expression on the bottom. And now we get to the 4 steps obtaining the final transformed equation. From Euler's equation, which governs the inviscid flow at the boundary layer edge, we may write this simple expression. No comparative with all figures, right? Denote the rho mu ratio by as a C proportional to rho mu over rho E times mu E, and grouping terms in this equation, we finally obtain this expression on the middle of this line. This equation is a transformed boundary layer x momentum equation for a two-dimensional compressible flow. The boundary layer y momentum equation, stating that the dp over d eta should be equal to 0, becomes in the transformed space here. The boundary layer energy equation, even boundary equation, can also be transformed and defining a non-dimensional static enthalpy as this form. Here, H sub E is a static enthalpy at the boundary H layer edge. And utilizing the same transformation, we become the equation on the board. Here, Pronto, proportional mu Cp over K, and as before, C, it should be the same as a rho mu over rho sub E times mu sub E. By the way, in some literature, C capital is called the Chapman-Roubaixin factor. So this, our final, the last equation, is left as the sum of yours to prepare as a home for, as you want to your experience as the physics and derivation. Okay, so, and let us examine our last equation on this slide, and they are transformed compressible boundary layer equations. They are still partial differential equations, where both f and g are functions of zeta and eta. They contain no further approximation or even assumption beyond those associated with the original boundary layer equation. However, they are certainly in less recognizable, somewhat more complicated looking form than the original equation. But do not be disturbed by this. In reality, all this form that will prove to be practical and used in the following discussion. Indeed, transformed equations will occur frequently in our presentation of hypersonic viscous flow. I mean, not only in our part 2 studied here, but also in our discussion of high temperature chemically reacting flow in next part 3. And thus, it is important to understand and feel comfortable with this equation. So, the preceding transformed boundary layer equations must be solved subject to the following boundary equation. The physical boundary conditions were given immediately following all these equations. The corresponding transformed boundary conditions are as follows. At the wall, for fixed wall temperature, we can write this simple expression here. For adiabatic wall here, at the boundary layer edge, we may write this expression. Okay? In general, solution of our equation, along with the appropriate boundary conditions, yield variations of velocity and enthalpy throughout the boundary layer. And the pressure throughout the boundary layer is known because the known pressure distribution, or you may say equivalently the known velocity distribution at the edge of the boundary is given by very simple PE, it's a function of zeta. And this pressure is impressed without change through the boundary layer in the locally normal direction, which says that pressure should be equal, constant, in the normal direction to any zeta location. By the way, this is the usual boundary layer result. But keep in mind that here we are ignoring the possibility discussed a bit earlier, that a finite normal pressure gradient can occur in hypersonic boundary layer. And finally, knowing H and T, enthalpy and pressure, throughout the boundary layer, equilibrium thermodynamics provides the remaining variables through the appropriate equations of state. For example, temperature dependent from enthalpy pressure, rho, from enthalpy pressure, etc. So, for convenience, it is useful to visualize solutions of our equation displayed as profiles through the boundary layer as various locations of zeta, as qualitatively sketched in this slide. At the top of this slide, velocity profiles, I mean eta as the coordinate and u as the abscissa horizontal, ordinate vertical, right, are shown at 3 different stations along the surface. In our case, denoting as the zeta 1, 2, and 3. At the bottom of this figure, static enthalpy, eta as the ordinate, yes, you see eta as the ordinate, and the H enthalpy as an abscissa, right? Are sketched as 3 different stations. In general, even though these profiles are calculated in the transformed zeta and eta space, they will be different profiles at each different values of zeta. So boundary layers that exhibit this behavior, which is the case in general, and called non-similar boundary layer. This is contrast to the concept of a self-similar boundary layer illustrated a bit earlier, as I show you repeated in this figure, and which is a special case that will be discussed in subsequent paragraphs. Including the general boundary layer solution, such as sketched here, are the velocity and enthalpy gradients at the wall, given by f second derivative from f and g first derivative. From the point of view of applied problems, this is the real payoff from a boundary layer solution, because the local surface in friction coefficient T sub f in friction coefficient is related to the second derivation from f, and the local heat transfer rate of the surface is related to the g first derivative. And these relations are obtained as follows. So the local skin friction coefficient Cf may be defined as this simple expression, right? Here we have the tau sub W is the local shear stress at the wall, and given this expression. Combining these last two expressions on the top and utilizing the transformation given by our equation before, we can obtain Cf in a more complicated graph. Or after simplification, we can get this expression on the middle, on this graph. The local heat transfer coefficient can be expressed by any one of several defined parameters, such as the Nusselt number, nu, we have Nusselt number, and Stanton number, Ch here, defined as follows two expressions. Here the Qw is the local heat transfer rate, I mean energy per second per unit area, at the wall, so W. X here is the distance along the wall measured from the leading edge. Here we have another coefficient K sub E is the thermal conductivity at the edge of boundary layer. T sub AW and HAW are the adiabatic wall temperature and adiabatic enthalpy, respectively, right? Adiabatic wall temperature and adiabatic enthalpy at the wall when the heat transfer to the wall Q sub W equals 0. Sometimes T sub AW is referred to the equilibrium temperature or equilibrium enthalpy, respectively. So from the definition, and noting that enthalpy is equals Cp times T, for calorically perfect gas, we may represent Nusselt in this expression on the right side. Or after simplification, Nusselt will be Ch times Reynolds times the price. I remember you Ch, it's a Stanton number. Stanton number, Ch, okay? So let us concentrate on our Stanton number, because Nusselt is related to this Stanton number, and the Fourier equation for heat conditions, namely by this equation on the bottom. According to this, we can build our Stanton number in this expression on the right, a bit very light. And using transformation, this becomes a bit more simpler as a second part. Or after next transformation, we can understand the number in this form of the middle. In summary, all these equations express the skin friction coefficient and the heat transfer coefficient and the wall. In terms of second derivation, should be equal 0. So there is no way of obtaining second derivation and first derivation at the wall directly. Only a complete solution of the boundary layer will provide the results at the wall. The main practical results of any boundary layer analysis. So the actual solutions, our equation of this frame for a general non-similar boundary layer requires the solution of coupled nonlinear practical differential equation as a two-point boundary value problem. In our case, the two boundaries being eta equals 0 and eta equals infinity, for eta at least large enough to be outside the boundary layer. These matters will be discussed in our future lectures. Not too much, maybe next or the next one. In the remainder of the present module, as a simpler approach will be considered. So we will examine cases where the boundary layer is self-similar. And that is where the picture shown in this slide falls. So we will consider two classical aerodynamic problems: flow over a flat plate and flow around a stagnation point. Okay? I think it's enough for today. Okay? And I hope you enjoyed our lecture, and I'm looking forward to seeing you next time. Bye.